So the problem is the following. So after pouring some liquid nitrogen into a mug, you notice that it creates a mist. So we start here by just having a quick look at what the problem is talking about. And so we can see that this is the phenomenon right here. And this fog has fluid-like behavior. It is stable under some conditions. And this is our starting point. So now, in order to investigate the phenomenon, we will be focusing here on three main questions. What is the fog made of? How is the fog created? And what governs the height of the fog? The problem here is complicated in a way that it combines thermodynamics and dynamic fluids and all of that. So the equations here are hard to put in place. So we prioritized for this presentation a presentation that focuses on understanding the problem via an experimental approach. Now, first question, what is the fog made of? So we, as first experiment, what we did is we tried to measure the temperature of the fog. And we found out that it is about -3 degrees Celsius, but this is just about, well, 0 degrees Celsius. And at this temperature, the only component in the air that undergoes a phase transition is water. So what we did is we tried to test this hypothesis. At first, a very simple test. What we could do is just spray some water onto the beaker. And what we saw is that the fog became much thicker and much more visible. So this is a good indication that it's probably water. Another thing we did is we put this beaker with the nitrogen into an inert atmosphere. So in this case, it was argon. And we saw no fog creation, meaning that it has to be something that is in the air that creates the fog. And this, I think, goes to show that indeed the fog is simply created by water. So we run with this idea in head for the rest of our experiments. So first, second, how is the fog created? The fog comes from this phenomenon. So we assume that there is some heat transport from the exterior, from the room temperature into the liquid nitrogen, which is at -200 degrees Celsius. And since it heats up, it emits, a gas of nitrogen. And this gas just flows out of the beaker and on the sides. We assume a few hypotheses for the sake of the experiment. So for instance, radial symmetry, we consider that the amount of heat being transferred into the liquid is small enough for us to consider that this is a quasi-stationary system. We consider a constant mass flow rate because of how the beaker is being heated, and also laminar flow. This is basically how we can get an idea of what's going on. So the speed inside of the beaker is perfectly vertical. And then the liquid pours out just with a radial component out of the beaker. Since the liquid nitrogen, or maybe the gas nitrogen is cold, it's denser than the rest of the air, and it falls down when it gets poured out. Now, with those hypotheses I talked about before, we can deduce that there is a stratification of temperature inside of the beaker. So as follows, and we know that the temperature gradient moves by sections up to the top, well, from -200 degrees up to the top to 0 degrees. Now, so with all of the information in mind, we can find what creates this fog. So inside of the beaker, there is no air, meaning that there is no water simply to transform into ice. So here, the fog cannot be created. On top here, the air is too hot, so no fog can be created. But right here, in between those two regions, there is a sweet spot where the temperature is just enough for the water to condensate into ice. So that's why we see this thin layer of fog. So this experiment that we did here confirms that the fog is created out of something that is in the air, because we put some aluminum foil around the beaker, and as we can see, the fog is just simply sitting on the foil. Now, on to our last question is what governs the height of the fog? And what we did is a simple experiment where we cut out some form of some shape into a cardboard. In this case, this is a square opening, and we can see on the video that the height of the fog is just a little higher than the rest of the fog, like on the sides. So this makes us think that maybe the opening has something to do here with how the fog is created. We tried several different openings here, for instance, dot openings and slit openings, and consistently the fog is being projected higher than as if it was just an open beaker up to the air. So the conclusion we get here is that the height is related to the speed of the gas simply coming out of the beaker. So this begs for this thought experiment. We consider two different liquid heights. So the liquid nitrogen has two different heights. Would this affect the height of the fog? Now, if we think about this, so mass flow rate is conserved in both cases. It's approximately the same, meaning that the volumic flow rate is approximately the same at the top, and the gas speed is approximately the same at the top too. And the fog height shouldn't change. The experiment we did to test that was the following. So we just poured some liquid nitrogen into a beaker, and we waited. We waited 300 seconds for the liquid nitrogen to go down. And as it was going down, we measured at every point in time the height of the fog. And what we saw is that in this region right here, the height of the liquid was varying. As we can see on the video, the height of the liquid changes drastically from 100 seconds to 300 seconds. But we recorded no change in the height of the fog. So meaning that indeed height of the liquid isn't the main parameter, and this goes in the same direction as our little thought experiment earlier. Now, something we observed too that seems to contradict what I just said is that when we move the beaker around, the height of the fog seems to be following the height of the liquid. But this is weird because I just said that for two different liquid heights, the fog height shouldn't change. But what's actually happening here is when you think about it, the liquid is pushing the column of gas that is above it when it's moving up, and this pushes the fog up too. Same thing for when the liquid goes down. Also, the fog goes down because of the whole column of gas is going down too. So this is actually also going in the same direction as our conclusions, as our earlier conclusions. So now to conclude, I asked 3 questions at the beginning of this presentation. So the composition of the fog, and we found out that is water actually condensing into ice. About how the fog is created. So it is created because of the meeting point between the hot air and the gas that is made only of nitrogen. And now what governs the height of the fog, we found out here that the main parameter is simply the speed of the gas flowing out. Thank you for listening.
So, dear colleagues, my name is Alonik, and now I am opponent of the problem number 11, flat fog. So let's talk about a little bit about the statement of the problem. So we say that under some conditions, if we put the liquid nitrogen into the mud, we may see that it vaporizes, and we can find the clearly marked thin plane with certain height. So what does the statement of the problem talks us? First, it talks that we should think about how to visualize the flow and make contrast of this plane of flat fog plane higher, and also maybe to control some random flows which can be caused by, for example, if I move my hand like this near the mud, it can it can change the shape very. It can really change the shape. So it's so first because later in discussion we will start it with points to improve reporters' experimental setup, and also we're asking setting of the problem to think about scene of the plane and height this plane is located at. So in the report we had some investigation about the height location, the height of the plane. For example, reporters change focus. How does it depend on time? And he could see that it decreased by the time. But unfortunately, reporter missed one point of the problem about the scene of the plane. So this is one of the points to improve in the report to take it into account, at least experimentally. So now let's talk about the main results which were done by report. Firstly, he saw that he talked about fog composition because of he could approximately measure the temperature. But I think it was not of measure the temperature was not exactly correct because, in my opinion, we have showed some radial distribution of the temperature. So temperature should change by the radius, and the reporter measured it just on a certain height. So I think that accuracy of measurement temperature in this case is pretty slow, and it's better. And it would be better to measure radial distribution of the temperature, not try to measure it for whole plane. Also, he showed us a model with of this phenomena in case of radial symmetry. So we agree with this assumption. Is this correct? Also, we think that quasi-stationary assumption is correct, but not in all range of parameters which you can have in this problem. Next assumption was about constant flow rate, but I don't think that it's surely correct to talk about it because it would be good to try to, for example, put your mark with nitrogen on the weights and try to measure how does the weight change with time. And from this, you may clearly get the UMS flow rate and check if it is really if it is constant in the experiment. So it would be really good point to improve. And finally, about Lemon, there was told that we'll work with laminar flows, but I think it's incorrect to say that your laminar is flow without trying to measure the Reynolds number of the system, because how your flow looks like will depend on this dimensional parameter. Also, we consider the shape of the fork, and we could clearly see that it's some iterate in the center, and there are edge effects on the backs, so it's really good point. We saw how the height changed with the time, but also we saw that height of the plane is not the key parameters, but we will say what is the key parameter of this in this case. And here we go to the main points of report. So strong points was qualitative heat exchange on qualitative level, and also trying to talk about temperature distribution on qualitative level, and good qualitative agreement with experiment. Also, I think we stated height of the plane as function of time, but there are some points to improve. For example, try to find critical Reynolds number, see what happens with high Reynolds number, and for example, use flow visualization to model up your setup, take into account thickness of the plane, and also make some experiments with humidity. So now we are going to discussion. And first,
so you finish now, right?
Yeah.
You finish up now.
Yeah, because
Thank you.
And firstly,
Yeah,
I'd like not to switch off my presentation and show you some kinds of some things I'd like to recommend you to improve in your setup. For example, as you could see from your experiment, mat with the fog was not in some special aquarium. So all random flows, for example, if I move my hand like this, they can affect and change shape of your fog. So I'd strongly recommend you to use something like this plastic aquarium or glass. In this case, no one random flow can affect the phenomenon. So very important. Do you think that aquarium would be a good improvement of your work, of your experimental work?
So I think here it might be an overkill to actually put everything in a box, since the phenomenon of the flat fog was actually quite stable, as I showed in the beginning. And the level of precision I was going on from my experiments was of the order of like a millimeter. So in most cases, this was, I think, good in, I mean, the setup I had was good enough.
But don't you think that it's possible to improve your stuff? So I agree that it was good enough, but don't you think that it's possible to improve it, to make it even better?
So yeah, maybe enclosing this mug inside of a jar might help investigating things that happen maybe near the beginning when you pour the nitrogen into the cup and it's boiling. So this is where the most uncertainty comes from in the height of the fog. And I think that enclosing this might improve the visibility of those first seconds.
And if you talk about the visibility of your system, one more thing I'd recommend for you, just for making the setup even better, is maybe to try laser visualization of the flow, because in this case, accuracy of your you could clearly visualize all the flows in the system, and it would be really good improvement for my opinion.
So now the laser is used to measure the height of the fog?
And visualize the flows. Visualize the flows.
Okay, okay.
And so now...
Okay, I don't like any questions about how to improve the setup of the reporter. Just please stick to the reporter's setup, right?
What?
Try to stick to the reporter's setup.
Yeah, like this. So, reporter, the reporter, let's talk a little bit about how does your fog raise? So, what is the mechanism of its raising?
Could you repeat that last part, please?
Yeah, what is the mechanism of raising nitrogen from the mug? Why doesn't it just locate in the mug? Why does it go outside and raise?
Why doesn't it go up, the gas nitrogen?
No. Yeah, the question is, why does it go up from the mug?
Oh, because it heats up. I think that's it. It heats up. It produces more and more gas nitrogen, and the new created gas is simply pushing out the old gas.
So I agree that heating plays some role, but don't you also think that there is some additional pressure in the mug because of the nitrogen evaporation that can additionally push your nitrogen gas?
In terms of pressure, I don't know exactly how pressure behaves in this system, actually. All I know is that the volumic mass of the gas is changing greatly since the moment it was formed until the moment it is ejected. But the pressure I haven't investigated.
Okay, so I strongly recommend you to try to take into account in your model in order, because it can help you to predict the height of your plane theoretically. So I think it's helpful for this way to improve your theory.
Okay. Also, could you go back to like the slides where you addressed a few of my talking points? I would like to respond to those.
Yeah, of course. Just wait a second.
And also, so you asked me about the Reynolds number, and I was wondering also, do you have an estimation for the Reynolds number in this case?
So I think that it really depends on the parameters. For example, it depends on the temperature on outside temperature, because it affects the velocity of flows raising. Also, the area of your nozzle affects the Reynolds number. So because of it, I cannot.
Okay, so assume for instance, a system at room temperature with an opening that's just a classic glass opening. You have a normal glass. Do you have an answer for that, or?
No,
I would like to say we can invite team members to the discussion.
Yeah, so if
we talked
anyone...
about the influence of temperature also on the system, and I think this can be explained by my model. If you increase the temperature of the room, you actually increase the amount of heat that is being given to the liquid, And this means that there's more and more gas being created faster and faster. So it should actually increase the height of the fog because more and more gas is pouring out.
I agree with it. So if any member of the team have some questions, so just write plus in chat. I'll see it and ask you about the query question. Okay. As there are now, since there are no questions, let's go to the your plot from your presentation, where you show us how the height of the fog changed over the time. So can you? It was decreasing on 90th frame. Can you please open it? And so I want to talk with you on qualitative level. Why is it go to some stationary
Okay, so
position?
oh, excuse me 2 seconds. I just need to put on the slides. So as you saw on the graph, it was height of the fog against time, and the height of the fog was actually decreasing at first. And I think this is due to the fact that the system is still adapting to the heat of the MOG and is receiving more heat just from the MOG than just by normal heat transfer in the stationary phase. So the stationary phase is characterized by the fact that the MOG's temperature after you pour the liquid nitrogen adapted to the liquid nitrogen. And the height that is increased at the beginning is simply due to the MOG heating up. Okay,
so now it's clear for me. Next, there are questions in the chat. So let's talk about the thickness of your plane. So instead, the problem I say that there is some thickness of the plane, which would be interesting to investigate. So don't you think that such parameters, for example, as humidity, can affect this, your plane thickness?
Yeah. And this would actually also be confirmed by the experiment I showed earlier when I sprayed some water onto the beaker. We could clearly see that the thickness of the fog is increased.
Yeah, and sorry for interrupting you, but as you agreed that humidity is important for thickness of, don't you see? So are you sure that humidity was the same in all your experiments? Maybe because it can change in you if you just make it with your setup without adding it some aquarium or liquid.
Yeah, that's true. It may change. I didn't check for the humidity, but what it influences mostly on is, I think, the thickness of the fog. And since I was looking for the height, it didn't make a difference, I think, in my results that I was looking for. But indeed, yeah, the humidity might change how the fog behaves.
Okay, so now we have one question from the chat. So Ivan Kolesnikov asked a question.
So my question is the following. So you stated that the humidity is the crucial factor in this fog formation. Am I right?
The fact that water is in the air is crucial, yes, for the fog formation.
Okay, so the question is, didn't you try to put your setup into dehydrated atmosphere?
Like, I did. I showed it in my slides, actually, in the beginning. I did the experiment under an atmosphere of argon. So it clearly showed that there was something in the air that was creating the fog.
Can you please show this slide once again?
Yeah, sure.
Okay, thank you very much.
Wait.
Any more questions from teams? Really, we don't have any teams in the discussion. Any team member?
I'm actually wondering, because you actually investigated, I think, how the fog behaves for systems that don't have laminar flow, and you seem to maybe have some insight into that. So I'm curious to see what would happen if you consider higher Reynolds number.
So do you get the question? Answer the question.
Yeah.
Okay, so and just no question at the least. Do you think that area of your mark can influence the height of plane?
Could you repeat?
Do you think that area radius of your mark can affect the height it goes up?
You mean
like if you take small or big marks with all the same initial parameters?
What parameter do you?
Radius of your mark.
The radius.
Yeah,
the radius of the mark. I don't think it should that much influence on the height of the fog, since it's mainly due to the heat transfer to the MOG, and what affects the flow is the aperture at the top, because it affects the outward speed.
I have a question. Do you think that from both the opponent and the presenter, that do you think that it's the nature of the liquid nitrogen, or can you produce this flat fog from other things as well, like for example dry ice, if you use that in solid form, which can you produce flat fog from there?
You mean using another substance?
Another material, yeah.
Okay, so I think since this problem, the creation of the fog doesn't depend on what's inside actually, but just on the fact that inside of the MOG there is no air, and there is a flow, a constant flow out of the MOG. I think that using another source of dry and cold material would create a similar effect.
Okay, yes. Do you have any other idea, presenter? Sorry, opponent.
So I agree with the reporter in case that we can observe this with other substances. For example, is for fluid ice. But I think that it's very important to have a big enough heat exchange and heat transfer between this gas, which we get from dry ice, and the air, which is outside the MOG. So that the heat transfer is should be the most important in this case.
So can you find the temperature limit after which it will start forming the flat form?
I think it can be done analytically while knowing all constants of the used materials.
Okay.
Okay, thank you. Zahar, do you have any question to report?
Yeah, I have. To the reporter, I understand your reasoning why the air is crucial in this problem, why the air creates the fog. But how do you distinguish between the liquid water, for example, and ice, which you claim to be the reason of the fog? So why do you think it is exactly ice, but not the liquid water?
Because fog is made of ice crystals, and at this temperature, this is the phase transition that corresponds for water to go from liquid to solid.
Okay, the temperature. Okay.
Okay, thank you. Leandro, now you can go with your question.
Yeah, this is a beautiful problem and it's very hard to work, but I have the feeling that you identified that a very important parameter is the heat flow to the vessel. And the question is both for reporter and opponent. Can you devise a way of controlling the heat flow to the vessel in order to change the fog height and perhaps change the Reynolds number as well?
Yeah, so maybe somehow heating up the liquid nitrogen by inputting some sort of source of heat inside the beaker. Obviously, would need to find some equipment that is adapted to work in those temperatures. But if you can manage to do that, you can quite easily manage to control the heat that is going into the beaker by controlling, for instance, the power that you input into your device. And if you work in a beaker that is isolated from the outside, I don't remember the name, but a beaker that doesn't let heat to go as much through as normal glass, then you could maybe neglect this phenomenon compared to the phenomenon of your device you're inputting into the liquid.
And for my opinion, I think that if it will depend on what mark we use. For example, if it is really long, as this one, in this case, heat exchange with the vessel can take important role. But if we'll use very short, like with this height, will be our mark. In this case, heat exchange won't play important role. So it really depends on how does our mark look like. If it's like tube long, it's important, only in this case.
Thank you. And Sonia, you have time for your question.
Yes, I would like to ask to the reporter a clarification. At a certain point at the beginning of your presentation, you show the container where there is your liquid nitrogen, and you said that there is an exchange of temperature, if I well understood, between the external part and the inner part. Am I correct?
Yes.
Can you put the slides? So now what happens if you use a thermos? So,
Yeah, so
you avoid this exchange, because as far as I understood, all your result is based on this. The fact that there is this exchange, so you have this gradient of temperature from the lower one to the upper one.
All those experiments I showed were actually made in a thermos. It was isolated from the outside, but a perfect thermos doesn't exist. So there's still some heat going in. And the reason we used a thermos is because the experiment was simply longer and we could make more observations on the fog. So those experiments were made using an isolated system.
It would have changed something, or simply the time, also to the opponent, in case.
Yeah, no, it probably would be slower the reaction would happen faster in something that is not isolated, and probably be more all over the place because of the boiling, etc.
The opponent,
and from my opinion, I think that it will affect mostly only the time needed. So on the time when it will change.
Okay.